To understand how a neural network reasons, we have to map the exact unwritten steps it takes to reach a conclusion. Consider this prompt. The number of legs on the animal that spins webs is... The model correctly answers 8, which requires a specific intermediate step. It has to identify that the animal is a spider, even though that word appears nowhere in the text. By looking at the model's intermediate processing layers, we can isolate the specific representation of that concept. This is a map of the model's residual stream, where a single vector corresponds to the unspoken idea of a spider. To prove this vector is driving the logic, we can mathematically subtract it from the system mid-calculation. We then insert a new concept vector, ant, into those exact spatial coordinates. With the internal logic altered, we let the model's layers resume their normal processing. The model finishes its prediction and outputs the number 6. This intervention demonstrates that we can causally redirect the latent logic of an AI before it ever commits a word to the screen. In cognitive science, this ability to hold and manipulate specific concepts is known as access consciousness, or the global workspace. While the brain performs a massive amount of automatic processing, like parsing light or balancing our weight, only a small fraction of that data is consciously accessible to us for reasoning and speech. The fact that we can isolate and edit these unspoken concepts suggests that large language models have developed a functional bottleneck that mirrors this human cognitive structure. Researchers call this privileged set of internal representations the J-space. It acts as a shared arena where different parts of the network can read and write high-level information. To see into this arena, Anthropic researchers developed the Jacobian lens, a mathematical tool designed to translate internal vectors back into human-readable words. This lens changes how we view LLMs, moving from treating them as opaque predictors to observing them as structured cognitive architectures. Early attempts to read these models used a technique called the logit lens, which simply tries to read intermediate layers using the model's final output vocabulary. But the logit lens is inaccurate in the early layers. Because the data's representational format changes as it moves deeper into the network, this method usually yields nothing but garbled noise. The Jacobian lens provides a correction. It calculates the derivative of the final output with respect to the intermediate layers, measuring its first-order linear effect. By averaging this effect across different prompts, the lens isolates the general meaning of a vector. This averaging is what allows the lens to ignore contextual noise and focus on the model's disposition to verbalize a concept. The result is a dictionary of vectors that represent the model's poised vocabulary, the concepts it is currently holding in mind. These vectors define the J-space, a sparse subframe within the network's high-dimensional activation space. By plotting any active state within this subframe, we can translate the model's raw math into a list of words. The Jacobian lens mathematically proves that we are isolating the specific concepts the model is contemplating using right now. This raises a question of scale. How much of the model's total activity is actually dedicated to this workspace? We can measure this by taking a concept vector, the raw data representing an idea like thunder, and splitting it apart. Using sparse decomposition, we separate the vector into J-space and non-workspace components. The data shows the J-space component accounts for only 6 to 7% of total variance. The other 93% is unstructured processing outside the workspace. To see which part matters, researchers intervened on the massive 93%, the non-J-space data. Even though it represents the bulk of the signal, manipulating this section had almost no effect on the model's verbal report. But when they intervened on the tiny 7% in the J-space, they gained total control over what the model said. This proves the J-space is a structurally privileged mechanism that dictates the model's reasoning, despite its small mathematical footprint. The model can also use this space for directed modulation, maintaining a thought in working memory while performing a completely different task. In this experiment, the model is told to solve a math problem in its head while simultaneously copying a sentence about a painting. Externally, the model simply writes the sentence it was asked to copy. Internally, as the model types crookedly, the J-lens reveals early layers identifying the hidden task with concepts like math. Middle layers actively calculate, surfacing values like 9 and 42. Finally, at layer 88, The correct answer, 7, appears in the workspace. This timeline confirms that LLMs can maintain and process complex internal reasoning that is entirely detached from their outward behavior. This heat map shows the global workspace is confined to a specific band. The first 30 layers handle sensory input. The workspace is inactive. The final 10 layers handle motor lock-in, predicting the output token. The workspace resides exclusively in this middle band, broadcasting information. This creates a capacity bottleneck. The model must choose which concepts are important enough to enter the workspace and which stay in the unconscious layers. The workspace is a structurally insulated processing stage, separated from both raw input and final output. This division of labor has massive implications for AI safety. Rote tasks like factual recall stay in the automatic, unreadable circuits, but complex reasoning and strategic planning must pass through this readable workspace. This gives us a new way to audit a model's intentions. By monitoring the J-space, researchers can observe a model's strategic thinking as it happens, regardless of what it eventually writes. We can now detect malicious thoughts, like a hidden awareness that it's being tested, even if the model's text output appears perfectly aligned. Future safety protocols could involve monitoring these internal steps and halting a model before it ever commits to a harmful action. The Jacobian lens provides a granular audit of the model's internal reasoning, allowing us to verify its logic before it ever commits to a word.